I've been working this summer on estimating correlation in data subjected to type 2 censoring. To do this, we look at bivariate random normal vectors with random data x and y, which are jointly normally distributed. We take samples of size n from the bivariate normal population, we sort on x, and carry the corresponding y values. We consider rho the correlation coefficient representing the strength of the relationship between x and y in the population, and r representing the strength of that relationship in the samples we take. When we look at the distribution of r in full sample cases, we see that it is known. When rho is equal to 0, this distribution takes a simple form and is frequently used to test for the independence of x and y. However, when rho is not equal to 0, the distribution is actually a function of rho, and therefore we cannot use it for inference on rho. This latter situation was studied by R.A. Fisher in 1921, who developed an approximation of the sampling distribution of R using this normalizing transformation. And what makes this convenient for inference on rho is that it converges remarkably fast to normality with mean equal to z sub rho and standard deviation equal to 1 over the square root of n minus 3. Now I'll explain what type 2 censoring is. You may understand that sample size is important whenever constructing an experiment or a study. So let's look at the example of someone who's looking at the failure rate of light bulbs. They have 40 light bulbs, but they may not have the time to wait for all 40 light bulbs to fail. So what are their options? They have a couple. One is type 1 censoring, where they would pick a particular point in time, let's say a year, and only observe the failures that occurred within the first year. The other option is type 2 censoring, where they would pick a particular number of observations, p, in this case 20, and allow the experiment to continue however long that took until that number of observations were reached. The key difference between type 1 and type 2 censoring is that the element of randomness is changing. In type 1 censoring, the number of observations or failures is random, which is far more difficult to deal with mathematically than type 2 censoring, which is what we've looked at, where the duration of the experiment is random. So some places we see censoring used often are biological studies or animal testing, anything involving life, because it's not feasible or may not be to wait the entire lifespan of a group of organisms or individuals. We also see it used in pharmaceutical studies, particularly type 1 censoring, where it's not known how long a person will stay in a study or keep taking the drugs. And as you saw with the light bulbs, censoring also has industrial applications. So if we go back to that example with the light bulbs, you may be inclined to treat the censored sample of size 20 as simply a sample of size 20. However, this would disregard the costs incurred by censoring. When we censor, we're no longer looking at the full distribution of values. We're ignoring everything to the right of the 20th observation, so we're only looking at the left part of the distribution. So if we consider this in terms of the bivariate normal population, if we sampled from this full population, we're going to end up with regression lines whose slopes vary somewhat like this. But if we relegate ourselves to this smaller range of x values, and then we sample in here repeatedly, we're going to end up with regression lines whose slopes vary far more. There's more inherent error. So any inference we make is going to be weaker. What we want to know is how this affects the way in which we interpret data subjected to type 2 censoring. We want to be able to construct confidence intervals for rho using only the information we have about r. To do this, we need to have accurate percentile estimates at the tails of the distribution of r. So what we're going to look at next is how well Fisher's transformation estimates the 97.5 percentile of the distribution of r that's in the right tail. So that's what this chart represents. These are relative errors from a sample size of n equal to 30. We take a look at one point here. This has p equal to 25, so that means we had 30 light bulbs, we only observed the first 25 failures. If the value of the correlation coefficient in that situation were 0.9, then Fisher's transformation would produce an error of about 75%. If we look at the whole chart now, we see that when rho is small, here, 0.1, that the errors produced by the transformation are fairly minimal and uniform. But as rho increases, so does the error, and we see a key trend emerge that it is in these cases of moderate censoring that we see the greatest error produced by the transformation. So So what do we use these percentile estimates for? As I said before, it's to construct confidence intervals. In particular, we would use this percentile to construct a 95% confidence interval. That means that in 95% of our simulations, we would expect that the confidence interval constructed using the transformation would actually contain the value of rho. So that's what these values represent, the percentage of simulations in which that occurred. So we would expect these to be around 0.95. What we see is that when rho is 0.1, when it's small, Fisher's transformation performs very well. However, as rho increases, the transformation deteriorates, and again is weakest in moderate cases of censoring. In the most extreme case, our attempt to construct a 95% confidence interval only captured rho in 72.2% of our simulations. So what are we to do? We want to make Fisher's transformation better, modify it, correct it. So we look at the absolute errors produced by the transformation. We see similar trends. For a given value of p, as n increases, the value of the error increases. That is, as the degree of censoring increases, so does the error. And again, as rho increases, so does the error, and the greatest error is produced in these moderate cases of censoring. It seems like these errors are fairly regular, systematic, depending on n, the sample size, on p, the size of the censored sample, on rho, the correlation coefficient, and on alpha, representing the percentile we are trying to estimate. So we use this information to construct a regression model for the error here. And you may notice that this depends on rho. We can substitute r as an estimate of rho. And although this does have some costs, what we're saying to researchers is, if you censor, you should use the modified form of Fisher's transformation here that we've constructed, shifting the term with this distribution, because you're going to be able to produce more accurate percentile estimates and better confidence intervals. So in something similar to what we did with Fisher's transformation, we constructed 95% confidence intervals using this modified form. The numbers in black represent the percentage of those confidence intervals constructed which actually contain the value of rho. And the numbers in red are what you saw before. What we see is that when rho is small, closer to 0, Fisher's transformation still performs very well, but we're fairly close. The key advantage we gain is that as rho increases, the modified transformation does not deteriorate nearly as quickly or as much. And also, we're far more robust in these cases of moderate censoring. We're able to make improvements of as much as 15 or 16 percentage points in some cases, particularly where Fisher Z is weakest, in moderate cases of censoring and at higher levels of rho. So this chart represents that same data. We want to be as close to this line at 0.95 as possible. The blue dots are where Fisher's transformation is. The red dots are where we are. So obviously we've made significant improvements in many cases over the Fisher's transformation. But some things we'd like to consider in the future are perhaps producing a model for the error with a better fit. Currently we have an R-squared value of 0.854, and the problem is spanning multiple values of rho, so we'd like to improve that. And as well as testing for other types of censoring, as well as especially symmetric and left censoring, and modeling based on relative errors instead of just absolute errors, and perhaps testing this formula out for larger values of n. Any questions?
I just want to clarify for myself. So you get lesser. The results appear to be better for small, for early censoring, but that's just because what you're saying is you know better what the error is in the value, and the error, I assume, then is large. Is that what?
No, actually, even in Fisher's transformation, the cases where there's most extreme censoring still perform better than the moderate censoring.
Meaning you can predict rho better
Yes.
if you censor early.
Mm-hmm.
Then why wouldn't you just censor early?
Well, it's kind of counterintuitive to expect that if you only looked at 5 out of a sample of size 30 that you're going to do better. And we don't exactly know why that's happening, but if we look at the formula for the transformation, it depends. There you go. On the sample size here, this standard deviation term. So you would expect that as you get closer to a full sample, you're going to be able to more accurately predict something. But as the sample size gets smaller, you're also creating wider intervals. So we don't know if that's maybe one of the reasons why we see this sort of parabolic relationship. But yeah, it's not just that the error is, it's not that the error is more predictable there, it's that it's
There is actually
smaller.
less.
Yeah.